Welcome to the ultimate guide to encryption, tokenization, and masking. My name is Billy Van Cannon, and I am Director of Product Management at Baffle. Here at Baffle, we've discovered that everybody has an idea about the differences between these concepts, but then when we start discussing what we do, we discover that there is no universal definition, and often the existing definitions are contradictory. We'll start off by looking at Baffle's definition of tokenization, which is synonymous with substitution and obfuscation. And that is simply that you are replacing sensitive data with non-sensitive data. The way Baffle defines it, lookup tables, encryption, and masking are all forms of tokenization. One definition I found states that tokenization is done with a lookup table and encryption is done with a mathematical algorithm. However, JSON Web Tokens, Apple and Google payment tokens all have tokens in their name, but they're created using encryption, not lookup tables. That's just one example. There are numerous similar examples where definitions don't match across the industry. Since there is no universal definition, it is best to look at your requirements. First, determine what you are trying to do, and then determine the best solution. Here are some suggested requirements to consider. And note that I'll often use plain text to refer to the original data and ciphertext to refer to the obfuscated data, regardless of how the data is transformed. So the first requirement is it reversible? Can you go from plain text to ciphertext and back to your original plain text? Do you want full or partial obfuscation? You can imagine times when you want the entire credit card number obfuscated, and other times when you might want to expose the last 4 digits so that your support team can identify their customers. Is a ciphertext format preserving? Meaning, does it have the same data type and length of the original plain text? Many times applications are written with a certain data type and length in mind, and if that changes, you can break your application. Can you do operations like sort, search, and math on the obfuscated data? The most convenient and secure way to secure sensitive data is to encrypt it within a database. But if your application then has to pull all the data, say the entire column, decrypting it and performing your operations, in the meantime, you have to write code in your application to do that, and you lose a lot of the security that comes with encrypting your database in the first place. So now we'll discuss several solutions and then compare them to our requirements. And along the way, we'll note other aspects to each solution. We'll start with a lookup table, or also sometimes called a vault. Here we have a lookup table with 3 different examples, and you can see that you have a lot of flexibility with a lookup table. You can really do the conversion in any manner you want to. Is it reversible? Yes, that's the point of the table in the first place. You can look up the ciphertext and then find the original plain text. Can you do partial obfuscation? Well, we did that here in this second example. The first 5 digits are obfuscated, and then the last 4 are in the clear. Is it format preserving? These first 2 examples are both format preserving in that they have numbers separated by dashes. Can you operate on obfuscated data? Well, in the case of a lookup table, the obfuscated data, it doesn't make sense to do math on that or sorts on that, so no. So special notes on the lookup table, and I think this one's kind of clear, is it almost doubles the infrastructure. You have a database that you're trying to protect. You have to create this new lookup table, which is another database in another location. And along with that, it means really you're moving the security concerns from one place to another. The next solution we'll look at is traditional encryption. Here we have a social security number, and we're using the AES algorithm along with a 256-bit key to output a binary. So is it reversible? Yes, we can take that binary, run it back through the algorithm, assuming the same key, and get our social security number back. Can we do partial obfuscation? No, in this case, the algorithm is all or nothing. Can we preserve the format of the original input? No, we can't, because the output is always binary. Finally, can we operate on the obfuscated data? Well, if you're trying to add a bunch of these binaries together, it doesn't really make a lot of sense. So most solutions you can't. However, Baffle has a way of doing this. So in the notes on traditional encryption, Baffle enables computation on encrypted data, and we call it real queryable encryption. Now, I'll talk about this a little bit in this presentation, but I'll have other presentations where we go into a deeper dive on that. Another aspect of traditional encryption is that you can embed metadata within that binary. So in this example, this first number right here is the index of our encryption key. It also allows you to do random or deterministic data. And it allows you to enter a digital signature for integrity. And I have separate slides to talk about those next. The last thing we'll touch on here is that traditional encryption is usually standardized. So if we're talking about the AES algorithms, we can go to the NIST documentation, specifically the FIPS 197 documentation. And the great thing about that is it means probably thousands of people worldwide have attacked this algorithm, and they've all come to the conclusion that it can't be broken with available means within a reasonable amount of time. We like to think of this as it being battle tested. So for a little more insight on the deterministic versus randomized encryption, let's say you're encrypting that same social security number, you have a given set of keys, and you encrypt it, and you get a given output. Then when you do that same encryption process using the same inputs, you get the same output. It's deterministic. However, if you have the same input and the same keys, and every time you encrypt, you get a different output, that's randomized. Randomized encryption is great for low cardinality data. Probably the lowest cardinality is something like a true or false question. Does somebody have diabetes? Well, if your attacker gets your database and they want to decode this, all they have to do is know one single person's condition. Does Joe have diabetes? True. Then they know the condition of everybody. And so randomized helps prevent that. The other thing about checking the integrity on the encryption is including a digital signature. So the way that works is, let's say you do the encryption in one location, and then you're transferring it to another location so that they can use the data on the other side. But along the way, a hacker intercepts this data, and even though we know it's confidential, you can't read the information. Let's say he wants to alter it just to cause trouble. And then the person who receives the data gets different information. Well, the digital signature will tell you that this is incorrect or that the data has been changed. It may not be able to get you back to the original data, but at least you can see that the integrity has been compromised and you can change course. The next solution we'll talk about is format preserving encryption, or FPE. So here we have 4 different examples, and as the name implies, it is encryption. And as a matter of fact, the underlying algorithm is AES. But instead of treating your plain text as a standardized set of bytes or blocks, it's now looking at this as a character by character basis, and then converting that into the character type that you like. So not only can you preserve the data type, like in this example, characters, you can choose whether you convert letters to numbers and vice versa, or some combination. So in this example, we're converting numbers to both lowercase letters, uppercase letters, and numbers, but we're preserving the last 4 digits. In this case, we're going from uppercase and lowercase letters also to uppercase and lowercase letters, but we preserve both the data type and the length. In this one, the 12 is a 4-byte integer. So even though it looks like there's different lengths, what really matters in this case is we're going from a 4-byte integer to another 4-byte integer. So as far as the requirements go, is it reversible? It's encryption, yep. So as long as you have the key, you can convert back. It allows partial encryption, as we show it here. Format preservation is the entire purpose of this algorithm, so it does do format preserving encryption. And can you operate on obfuscated data? And just like all the other examples, it doesn't make any sense to perform operations on the encrypted data unless you're using the baffle solution, which you can. As far as the special notes, it's specifically designed to control the data type and length of the ciphertext. And baffle even has a credit card version that passes the Loon algorithm. Many applications that take credit card numbers will run the Loon algorithm on them, and basically it's a check for typos. So now with FPE, you can send encrypted card data to these applications and not break it. Finally, FPE has been standardized specifically in NIST SP 838G. So we know it's a strong encryption and it's been battle tested. The next solution we'll look at is masking. Masking could be considered very similar to a lookup table, just without the lookup table. So you write a program to convert the data however you want, but you don't keep track of any way to convert it back. So as far as the requirements go, is it reversible? No, you can't go back from these X's to these ones, but you can do partial obfuscation, and you can make sure the ciphertext preserves the format, because again, you're writing this however you want. However, you can't operate on obfuscated data, because on the ciphertext side, there's no rhyme or reason that allows you to sort or perform mathematical operations. Now, as far as the notes on masking, there's 2 major approaches. There's static masking and dynamic masking. And we'll go ahead and look at different slides for this. So let's talk about static masking. Say you've got your data source with your original sensitive data, and you send it through some kind of obfuscation. I have FPE here, and I'll come back to that. But in any case, you obfuscate the data and you put it in your database. And then from that database, all your applications, regardless of the application itself or who uses it, gets that same information. Now, going back to FPE, you can use masking the way I just defined it. You can use FPE, you can use traditional encryption. It turns out it doesn't matter. In this definition of static masking, what matters is the fact that you're creating a trusted and untrusted environment. So on this side of the line, obviously there's access to the sensitive data. And on this side of the line, the data is effectively destroyed and everybody's getting the same information. And that's the static aspect of it. So a great application for static masking is lower or pre-production environments. So say your data source over here is your production environment database. You obfuscate the data and you bring it into another environment, say for your test engineers or your QA engineers or your DevOps or whoever, and then they can go ahead and stage and test out everything in a safe manner without worrying about the security aspects. So now this lower environment doesn't have to go through your security audits, and of course you don't have to worry about a security breach. Let's move on to dynamic masking. In this case, your database has the sensitive data. Now it can either be plain text or encrypted. It doesn't matter for dynamic masking. What matters is when you pull it out of the database, every different application and possibly even every user has a different view. And that can be in the clear, like human resources can see the social security number so that they can provide people benefits. However, there's no reason for them to see a social security number, so you pull that out. Same with support here. They don't need to see the entire credit card number or social security number for any reason, but they do need to see the last 4 digits of them so that they can identify their customers. And then this remote user doesn't get to see any credit card numbers or social security numbers, but they can still access the database. The next solution we'll talk about is privacy-enhanced computing. And it actually turns out this is more like a family of solutions. But here's the basic idea. You have your clear text data, and you want to perform encryption, but you want to do that encryption in such a way that now you can operate on the obfuscated data. So let's take a super simplified example. Let's say you want to find out the sum of all your encrypted data. So what you do is you go ahead and add the ciphertext up, this 234, 45638, 6239, get the result, and then you decrypt that, and you get the same answer as if you would have added the plain text. So the requirements, is it reversible? Well, it's encryption with keys, so yes. Can you do partial obfuscation? No, there's no way you're going to be able to do partial obfuscation and be able to maintain all these things, so no. Is it format preserving? Well, if you're doing numbers, so decimals to decimal or integer to integer, then I believe so, but not for non-numbers. Can you operate on obfuscated data? Yes, that's a point of privacy-enhanced computation. Now, as far as the nodes, it turns out, as I mentioned, there's several different varieties. The one I described up here most closely resembles homomorphic encryption. There's other ones called structured encryption, multi-party encryption, and secure enclaves. However, the problem with most of these is they are orders of magnitude slower than traditional encryption, and they're just not practical for most applications. There's also no standards yet. So because they're in experimental stages or kind of the academic stages, they haven't been published and they haven't been battle tested yet. The last solution we're going to talk about is synthetic data. Synthetic data is very different than the other solutions we talked about in that you're not doing a point-by-point obfuscation. Rather, you're using the original data to create an entirely new data set. And hopefully this new data set has the characteristics that you're looking for. And that would include statistical similarities. So in this small set I have here, 100, 200, 300, and this output of 295, 99, and 211, we have very similar mean, median, standard deviation, min and max values. But of course, they're not the same. So as far as the requirements, is it reversible? No, you certainly can't do it on an individual basis, but even with the whole data set, you can't really go back to the original data set. Can you do partial obfuscation? Well, you can, but there really isn't any need for it because this new data set isn't sensitive in the first place. Can it be format preserving? Yes, as a matter of fact, I would assume you would do that in most cases. Can you operate on the obfuscated data? Yes, and that's the entire point. However, it's not the exact same data. So as far as the special notes, as I mentioned, it must be a data set, not data points. But one of the implications of that is, let's say in the original data, you get some new information. Let's say you get another entry of 250 and another one of 400. Now you have to use your synthetic generator to create a whole new set of synthetic data. The original data can be real, or you can create a brand new data set seemingly out of thin air with GenAI. Of course, that GenAI has been trained with data previously. Now, the whole point here is to provide analysts or to train GenAI with data so you can find insights but maintain privacy. The thing about these insights is your generator has to be aware of the goals you have in the first place. So let's say your generator knows that you have to have a very similar average for the entire set of data. But let's say you want to narrow it down for some reason. Let's say you're looking for everybody in a certain zip code and you want to find the average there. Will the synthetic generator know that beforehand? And so you have to build all these insights into your generator from the very beginning. Here's how you do it with Baffle using dynamic masking and real queryable encryption. So you start with an encrypted database and you have your data analyst connect through Baffle. You can set up dynamic data masking such that when your data analyst does a select age from customers, it comes back masked, and therefore they can't see individual ages of any of the customers. However, using real queryable encryption, the data analyst could put in a query like select the average age standard deviation from any of the customers where the salary is over $100,000. And then you can get those respective values back. So here's an overall summary of everything we've covered. We have all the obfuscation methods that we talked about, and then we have all the requirements across the top. As far as Baffle is concerned, we don't do the lookup table, and that's primarily because of the problem that I noted, where you're taking the security problem and moving it from one location to another. And then in that new location, you still have to worry about security. Not only that, we do format preserving encryption, and when you look at the requirements, reversible, partial obfuscation allowed, preserving the data type and length, and also being able to do operations on the obfuscated data, it makes sense to just stick with format preserving encryption. Traditional encryption is also used because it's very powerful and also some of the metadata that we talked about, enabling randomization and integrity checks. Baffle also does masking, both static and dynamic masking, but we don't do privacy enhanced computing, at least in the other methods that I talked about, which are very slow and not battle tested. Again, because we can do operations on obfuscated data using traditional encryption, we maintain the speed of traditional encryption, and it is battle tested. And finally, we don't do synthetic data, but we have plenty of other ways to allow you to get insights from the original data and yet preserve the privacy of that data. Thank you.